choose to go to the moon in this decade and do the other things. Not because they are easy, but because they are hard.
Godspeed, John Glenn.
Roger, 0G, and I feel fine.
Get my feet up. Okay, I'm out.
How does it feel for the United States to be the new record holder?
At last, huh?
When that baby lights, there's no doubt about it.
Liftoff. We have a liftoff. 32 minutes past the hour. Liftoff on Apollo 11.
Houston, Tranquility Base here. The Eagle has landed.
That's one small step for man, one giant leap for mankind.
Hello and welcome. This is Michael Annis, and you're listening to episode 117 of the Space Rocket History Podcast. And now, Apollo, Lunar Module Design. It's been a while since I talked about the lunar module, so I have a brief audio clip to review what has been covered so far.
And in the fall of 1962, U.S. aircraft manufacturers competed to build what became known as the Lunar Excursion Module, or LEM. One of the competitors was a small aircraft company on Long Island. The Grumman Corporation had already spent time and money investigating the idea of a dedicated lunar lander.
For well over a year, they had been studying this problem of how to get to the moon. And because they had been studying it on their own with their own money for longer than all these other contractors, they submitted a much more detailed design.
Grumman's proposal was made up of two distinct stages, each with its own engine. A descent stage would take the astronauts down to the lunar surface. And then, when they wanted to return, a tiny ascent module would separate, leaving the bulky descent stage on the moon, and return the astronauts to the orbiting command module.
They really understood that weight was so critical, you wanted to leave the heaviest part behind to get off the moon.
Mission completed. This final stage of the LEM would also be discarded. NASA liked it, and in November 1962, Grumman won the contract to build the most complicated and sophisticated spacecraft ever conceived. But the process had taken almost 2 years, and Grumman would spend the next 5 making up for lost time.
With the signing of the Lunar Module contract, the Manned Spacecraft Center and Grumman began the design and development of a vehicle that would land 2 men on the moon and subsequently take them off. When NASA selected Grumman in late 1962 to build this final piece in the Apollo stack, the landing craft was still a long way from a frozen hardware design, while the command module and service modules were evolving from Block 1 to a more advanced Block 2 version during 1963 and 64, the lunar module was also changing, moving toward the huge spidery-legged bug that later landed on the moon. Actually, Houston and Grumman engineers had spent a month in negotiations and technical groundwork before signing the contract on January 14, 1963. Then it took until March before NASA headquarters ratified the contract. But Grumman forged ahead, devoting most of the first 3 months to establishing a practical external shape for the vehicle. Fortunately, cooperation between NASA and Grumman got off to a fast start. In late January, officials from the Houston Apollo office visited Grumman to review early progress, to schedule periodic review meetings, and to establish a resident office at Bethpage, New York, similar to the one already operating with North American Aviation in Downey, California. Then, following a tradition that had proven effective in other programs, the Houston office set up spacecraft and subsystem panels to carry out technical coordination. Thomas J. Kelly directed Grumman's Apollo-related studies since 1960, earning for himself the title Father of the Limb. But even with Thomas Kelly's input, the vehicle that finally emerged was a design by committee that included significant suggestions from the Houston panels, notably Owen E. Maynard's group. Here's a clip from Thomas J. Kelly, Father of the Limb, discussing how the shape of the lunar module changed during design.
On a 250,000-mile trip, weight was critical. As the design developed from concept to hardware, the shape and structure changed in several significant ways.
When you compare these two models, the proposal model and the final version of the LEM, many of the differences that you see are the result of our desire to save weight on the lunar module. This proposal model had aircraft-style seats. We realized that we really didn't need seats in 0G or even 16G. So in this LEM and in the real LEMs, the crew was in a stand-up position. So
next I have a clip from noted aerospace historian Josh Stoff describing what happened when NASA and Grumman discovered they were trying to put a square peg in a round hole.
As the prototypes evolved, the one constant was change.
Astronauts come to Grumman to test the design, and what they found is that an astronaut wearing a square backpack can't fit out the round hatch. So Grumman deletes the round hatch in the front. They put instead a big square hatch.
Finally, in the spring of 1965, NASA, worried design changes would never stop, imposed a freeze.
But before we get too far ahead, let's return to 1963. Using Grumman's initial proposal for the lunar module as the departure point for continuing configuration studies and refining subsystem requirements, the team that had guided the company through its proposal spearheaded the new design phase. When Grumman assigned 400 engineers to this task, an optimistic air about how long it would take pervaded both at Bethpage and at Houston. The job took longer than the 6 to 9 months originally anticipated, however, because of special efforts to guard against meteoroids and radiation, as we have previously covered, and to incorporate criteria imposed by the unique lunar environment. Basic elements in Grumman's proposal remain the same. The lunar module would be a two-stage vehicle with a variable thrust descent engine and a fixed thrust ascent engine. And the descent stage with its landing gear would still serve as a launch pad for the second or ascent stage. One design group examined a small cabin with all equipment mounted externally, and the other group studied a larger cabin with most equipment internal. The finding of the two teams pointed to something in between. The spacecraft that ensued was ideally suited to its particular mission, embodying no concessions to aesthetic appeal. The result was ungainly looking, if not downright ugly, because the lunar module would fly only in space, Earth orbit, and lunar vicinity. The designers could ignore the aerodynamic streamlining demanded by Earth's atmosphere and build the first true manned spacecraft, designed solely for operating in the spatial vacuum. At a mid-April 1963 meeting in Houston, Grumman engineers presented drawings of competing configurations showing structural shapes, tankage arrangements, and hatch locations. Grumman and Houston officials then worked out the size and shape of the cabin, the docking points, and the location of propellant tanks and equipment. The basic structure and tankage arrangement was a cruciform, with 4 propellant tanks in the descent stage and a cylindrical cabin as the heart of the ascent stage, which also had 4 propellant tanks. Still to be resolved were questions of visibility, entrance and exit, design of the descent engine skirt, which must not impact the surface on landing, and docking and hatch structures. In late April and early May, Owen Maynard, Chief of Spacecraft Integration in MSC's Spacecraft Technology Division, summarized for Director Robert Gilruth the areas still open for debate, especially the landing gear and position of the landing craft inside the launch vehicle adapter. Another sticky question, he said, was the overall size of the vehicle, which dictated the amount of propellants needed to get down to the moon and back into orbit. The lunar module structure, especially the descent stage, would be wrapped around the tanks. As the tanks were enlarged, the vehicle design would have to grow to accommodate them. There was one ray of light, however. Marshall was talking about increasing the lifting capability of the Saturn V launch vehicle from 40,800 kilograms to 44,200 kilograms. With that capacity, the target weight of the lander would be pegged out between 12,700 and 13,600 kilograms, instead of the 9,000 kilograms listed in the proposal. One early concern, though not directly connected with external design, was the firing of the ascent engine while it was still attached to the launch pad, which was the descent stage. The concern was that the exhaust blast in the confined space of the ascent and descent interstage structures could have unexpected effects. Some observers feared that the shock of engine ignition might tip the vehicle over, and what would happen if the crew had to abort during descent, shed the descent stage, and then return to lunar orbit. This would require extra fuel, posing yet another weight problem. Scale models test in 1964 allayed some of these misgivings, but the real proof had to wait for a firing test in flight of a full-scale vehicle. Although the descent structure with its 4 propellant tanks appeared practical from the standpoint of weight and operational flexibility, the ascent stage was harder to pin down. Nearly 2 years passed before the cabin face, windows, cockpit layout, and crew station designs were settled. By late 1963, Grumman engineers had begun to worry about the weight and reliability of the 4-tank arrangement with its complicated propellant system. They recommended changing to a 2-tank model, and Houston concurred. Redesign delayed the schedule 10 weeks at an additional cost of $2 million, but the system was much simpler, more reliable, and lighter by 45 kilograms. Yet the change brought its own problems. Because oxidizer was heavier than fuel, 4 tanks had allowed the engineers to put 1 tank of each on either side of the cabin for balance. With only 2 tanks, some juggling had to be done to maintain the proper center of gravity. The fuel tank was moved further outboard than the oxidizer, giving a puffy-cheeked or chipmunk appearance to the front of the vehicle. Also shaping the face of the ascent stage were its windows. Windows were basic aids for observation and manual control of the spacecraft, and the pilots expected to use them in picking the landing site, judging when to abort a mission, and guiding the spacecraft during rendezvous and docking with the command module. The importance of visibility was recognized early in Houston's studies and stressed in Grumman's original proposal. In both, large windows afforded an expansive view. Grumman had featured a spherical cabin like that of a helicopter with 4 large windows so the crew could see forward and downward. This design was discarded because large windows would require extremely thick glass and a strengthening of the surrounding structure, and the environmental control system would have trouble maintaining thermal balance. Here's a clip on the windows decision from Josh Stoff.
Grumman's original design has a large spherical top half, the ascent stage, with these very large glass windows. Well, there's no way you could have those heavy glass windows. Weight was too precious, so they had to go to much smaller windows.
There were also seats. Well, in 0 gravity or 1/6 gravity, you really didn't need seats. So the seats were taken out.
2 smaller windows could replace the 4 larger ones, but the field of view would have to remain very much the same. To get the required visibility with smaller and fewer windows, Grumman had to abandon its spherical cabin design. The new cylindrical cabin had a basically flat forward bulkhead cut away at various planar angles. The large convex windows gave way to small, flat, triangular planes about 1/10 of the original window area, and they were angled downward and inward to give the crew the fullest possible view of the landing area. Grumman's change to a cylindrical cabin posed another problem. A spherical shape is simple from a manufacturing standpoint because of the relative ease in welding such a structure. The new window arrangement and front face angularity made an all-welded structure difficult. The Grumman design team wrestled with the new shape and in May 1964 adopted a hybrid approach. Areas of the critical structural loads would be welded, but rivets would be used where welding was impractical. Grumman neglected to inform Houston of the switch in manufacturing processes, but a Houston engineer noticed the combination of welding and riveting while on a visit to Bethpage. Toward the end of May, there was a series of reviews and inspection of Grumman's manufacturing processes. NASA representatives looked at the welding criteria, mechanical fastening techniques, and the behavior of sealant compounds under temperature extremes and a pure oxygen atmosphere. The contractor demonstrated that its part riveted structure showed very low oxygen leak rates in testing. Although Manned Spacecraft Center officials tentatively approved the change, they left an engineer from the MSC Structures and Mechanics Division in Bethpage to watch Grumman closely. Marshall experts visited Grumman from time to time to extol the virtues of an all-welded design and to warn of the problems of mechanical fabrication. But the peculiarities of the lunar module made a mix of the 2 techniques almost inevitable. Now let's move along to the interior of the lunar module, starting with the cockpit. The lunar module's interior was as different from that of other manned spacecraft as its exterior, and it also took 2 years to design. A home on the moon required some very special features, such as equipment and procedures for rendezvous and docking, environmental control for living, an easy means for exiting and re-entering while on the moon, and the capability of operating in a low-gravity or no-gravity environment. With an internal volume of 60 cubic meters, the lunar module would be the largest American spacecraft yet developed. It would also be the most spacious, except for the command module when the pilot was there alone. To lessen already formidable crew training demands, Houston pressed Grumman to make the cabin instruments and displays as similar as possible to those of the command module. Complete duplication was impossible, however, because the two crafts were so different. Ground rules were laid down governing the degree of redundancy required in controls and panels. Although these controls would be duplicated on each side of the cockpit, some of the instrument displays would have to be shared by the crewmen. Above all, Grumman was told the spacecraft must be designed so that the hover and touchdown could be flown manually, and so that no single failure of the controls or displays could cause a mission abort. Because the lunar module was a means of transportation as well as shelter and living quarters for the crew while on the moon, cockpit design presented interesting problems to human factor engineers. The man-machine interface embraced such items as stowage of spacesuits and personal equipment, and room for the pilots to move about within the cabin. In a mock-up in mid-1964, 2 crewmen demonstrated that they could put on and take off their portable life support systems with suits either pressurized or deflated, reach for and attach umbilical hoses, and recharge their backpacks. The MSC Crew Systems Division drew up a document governing spacecraft, spacesuit interface, and change procedures. This was used by NASA to supplement spacecraft specifications and interface control documents. It was also an important managerial tool between Grumman and North American and the other major associates, MIT and Hamilton, the developers of the guidance and navigation system and life support system. The astronauts were an essential subsystem on the lunar module, and they were very much in evidence at Bethpage as well as at Downey, where they helped in the design of the command module. Scott Carpenter, Pete Conrad, and Don Isley were selected for the lunar module as their special assignment, and William Rector, the lunar module project officer, frequently called upon them for help. He also urged other astronauts to take part in the periodic mock-up reviews and significant decisions. This was not an unusual arrangement. Astronauts, being both engineers and test pilots, have played an active role in the design and development of every manned American space vehicle. An interesting example of pilot preference influencing spacecraft design revolved around including an 8-ball, or an artificial horizon instrument used for altitude reference in planes, in the lunar module. Grumman had proposed an 8-ball, assuming that the astronauts would want it. Arnold Whitaker recalled, quote, "The first thing NASA did was to say that there's no operational requirement for it. Take it out. So, we took it out. Then the astronauts came along and said, that's ridiculous. We must have it. So we put it back in. By this time, we were late. Dr. Shea had a program review and said, what's holding you up? And we said, this is one of the things. and he said, "Take it out. I'll accept the responsibility for it." The astronauts found out about it and said, "We won't fly a vehicle until you put it in." And NASA put it in, this time with a kit for easy removal later. Pete Conrad probably worked more on the vehicle's basic design than any other pilot as the configuration evolved. Rector relied on him to sound out the crews on cockpit features, controls, switch locations, and visibility, among others. One innovation which Grumman favored and which Conrad was instrumental in getting incorporated was electroluminescent lighting. An inherent problem in both aircraft and spacecraft had been light intensity that varied from panel to panel. This uneven lighting made it difficult for a pilot to scan his instruments rapidly and to adjust quickly to low-level exterior light conditions. Electroluminescence, a wholly new concept that used phosphors instead of conventional filament bulbs, afforded an evenness in intensities hereto unequaled in any flying craft. At the same time, it weighed less and used far less power than incandescent lighting. Conrad also got this new system into the Block 2 command module. The seating arrangements in the lunar module were perhaps the most radical departure from tradition in tailoring the cockpit. It soon became apparent that seats would be heavy, as well as restricted for bulky spacesuits. Bar stools and metal cage-like structures were also considered and discarded. Then an idea dawned. Why have seats in the lander at all? Its flight would be brief and the G-loads moderate, 1 G during powered flight and about 5 on landing. Since human legs were good shock absorbers, why not let the crew fly the lunar module standing up? So, as you have heard in previous audio clips, NASA engineers decided that astronauts could stand in the lunar module during the trip to the lunar surface. This concept was bandied about rather casually at first by two Houston engineers, George Franklin and Louis Richard. Franklin then met with Conrad to talk to Howard Sherman and John Rigsby at Bethpage. These Grumman employees in turn passed the idea along to Thomas Kelly and Robert Mullaney. At this point, the seat and windows problems merged. Standing up, the crew would be close enough to the windows to get a larger field of view. One engineer estimated it at 20 times greater than any other seating arrangement yet suggested. Moreover, since cockpit designers would not have to worry about knee room, the cabin could be shortened, saving 27 kilograms and improving the structure. Instead of seats, Grumman technicians devised a restraint system to hold the pilots in place during weightlessness and prevent them from being jostled about the cabin during landing. Resembling the harness used by window washers and linked to a pulley and cable arrangement under constant tension, it was augmented by handholds and armrest and by Velcro strips to keep the pilot's feet on the floor. Lunar module activities also focused on configuration control, schedules, and funds. In 1965, J. Thomas Markley, program control chief, directed the Apollo engineers to be more conservative in their proposals to the configuration control panels. Changes in the spacecraft must correct design flaws, not improve hardware. But stemming the flow of changes in the lunar module was not an easy matter. Many were required because of its mission. An example was the installation of fragile probes on the base of each footpad to tell the crew the lander was 1.5 meters above the surface and to switch off the descent motor. Because if the motor were still firing when the craft touched down, the engine nozzle would be damaged. Landing stability might be affected, and the ascent stage might be impaired by debris kicked up by the engine exhaust. One configuration issue carried over from 63 through 64 remained unresolved throughout 65, and that was whether to substitute an optical tracking system for the complex, heavy, and expensive rendezvous radar. In February of 65, the Configuration Control Board deleted the radar from the command module and added flashing lights to the lander. If the lone crewman in the command ship had to perform the rendezvous, he would use on-board optics, a ranging capability, and the VHF communications link between the spacecraft, which would also act as backups if the lander's radar failed. In mid-March, Klein W. Fraser of the Guidance and Control Division suggested replacing the rendezvous radar in the lander with an optical system as well, consisting of a star tracker in the lunar module, a xenon strobe light on the command module, and a handheld sextant for the lander's pilot. The substitute would offer two advantages: a weight reduction of 40 kilograms and a cost saving of $30 million. The Apollo office, hesitant to take such a step, decided to pursue parallel development. In mid-April, Grumman was instructed to design the lander to accept either system and to slow down RCA's radar development program. Radar tracker studies at the Manned Spacecraft Center would be completed by September, and a contractor would be selected to design the tracker. William A. Lee in Joseph Shea's office protested holding back RCA because the delay would force the deletion of the radar from the first and second landers that were planning to be used on Earth orbital missions. Lee said this would be a violation of the all-up concept of flying only complete spacecraft. But Lee's concerns were not taken too seriously. In August of 1965, Houston amended its contract with AC Electronics to include the optical tracker as government-furnished equipment. Grumman grumbled, but kept the spacecraft design flexible. 2 months later, MSC's Assistant Director for Flight Crew Operations, Deke Slayton, objected to the tracker because of its limitations in determining range, approaching and departing speeds, and the lack of experience in using the instruments. If an immediate choice had to be made, Slayton said, choose the radar. At the end of the year, Mueller, Shea, and Robert Duncan set up what they called a Rendezvous Sensor Olympics to be completed in the spring of 1966. If either system lagged, radar or optical, the decision would be obvious. If both were successful, Duncan's division would recommend a choice. If both failed, well, there would be a lot of work ahead. The optical tracker's lighter weight was attractive, since weight was an important factor in 1965. The lander had gained even more weight during the early months of the year than the command and service modules. In May, Shea persuaded Miller to approve an increase in lander weight to 14,850 kilograms, including crew and equipment. In June, Harry Reynolds warned Owen Maynard that it would be difficult to keep the spacecraft below that figure. All that summer, the warnings continued. Caldwell Johnson wrote Shea in August that the lander might get too heavy to do its job. The next month, Shea asked Houston's management for help in solving the problem. He also formed a weight control board, headed by himself, to act on reduction proposals. By this time, Grumman was really getting concerned. So, they launched a two-program attack known as Scrape and Swipe. Scrape meant just what the word implies, searching the structure for every chance to shave bulk off structural members. But Swipe Super Weight Improvement Program, SWIP, was Grumman's real war against weight. Grumman project engineer and father of the LEM, Thomas Kelly, led a SWIPE team of a dozen experts in structures, mass, property, thermodynamics, and electronics, whose task was to second-guess the whole design. This same team had recently and successfully shaved weight off the F-111B aircraft, and it knew what a tough job it was up against. When the SWIPE campaign started, the engineering design was 95% complete, so designers pored over already approved drawings looking for ways to lighten the craft. Grumman also pressured Houston officials to keep all government-furnished equipment for the lander within specified weights, and Bethpage scrutinized parts supplied by its subcontractors and insisted that these weights be reduced wherever possible. Weekly reports and monthly meetings between Bethpage and Houston turned into forums for airing suggestions for further reductions and discussions of what had been done. The first such review, held at Grumman on September 3rd, revealed that 45 kilograms had already been whittled from the structure by scrape. The more extensive SWIPE plan was outlined, including what had been started, what was planned, and what would be expected by way of evaluation and cooperation from Houston's Apollo subsystem managers. By the end of 1965, Scrape and SWIPE had pruned away 1,100 kilograms, providing a comfortable margin below the control weight limit. Now, one of the more striking changes to come from the drive for a lighter spacecraft was the substitution of aluminum mylar foil thermal blankets instead of rigid heat shields. The gold wrapping characteristic of the lander's exterior saved 50 kilograms. Here's a clip on the mylar.
Meanwhile, on Long Island, engineers were combating yet another hazard of spaceflight.
In space, you're facing the sun, it's 240 degrees. The dark side is 240 degrees below zero. You have to insulate the spacecraft as well as possible because there's huge fuel tanks in there. And the fuel's going to boil at 100 degrees and freeze at 30 degrees.
Such a huge temperature variation could also cause the craft to buckle. Yet Grumman couldn't afford heavy heat shields.
Fortunately, for the space program, DuPont had developed this new material. It was aluminized mylar. It was a gold color, and they found if you built it up to perhaps 25 layers, it's an excellent insulator.
The LEM was coated in mylar. To many engineers, the final vehicle was an insult to every notion of what a spacecraft should look like. But in the vacuum of space, it didn't need to be streamlined. It was one of the weirdest and most improbable flying machines ever conceived.
Many of these weight-reducing changes made the lander so difficult to fabricate, so fragile and vulnerable to damage, that it demanded great care and skill by assembling and checkout technicians. Structural components took on strange and complex shapes, requiring careful machining to remove any excess metal. A costly and time-consuming process, even after vendors had been found who would make these odd-looking parts. Thanks for listening to this archive episode of the Space Rocket History Podcast. If you are financially able, please support the podcast by going to the homepage, spacerockethistory.com, and clicking on the orange Donate button or the Patreon link. Thanks.